we will start from basic assumptions about the scenario of information retrieval, and in order to understand the axiom or constraint that the measure should satisfy. First, we have to take into account that information retrieval is more than sorting document. If it was just sorting, then we could use a Kendall correlation or something like that, an ordinal correlation coefficient, but this is more complex than this. Why? Because actually, when a system returns a ranking of documents, actually the system is discarding a huge amount of document. That is, we have an ocean of documents, and the user is like a frogman finding relevant documents in the ocean. In addition, so we have an implicit filtering task because every document that do not appear in the ranking are discarded. In addition, we have to assume that the frogman has a limited oxygen. So the idea is that we need to start from the idea that the more a document is located at the bottom of the ranking, the less it is likely to be explored by the user. And so this is not, as Stefano and Julio said, we have a lot of measures to solve this problem, and this is just the most popular measures in the state of the art. And now we will make a fast theoretical experiment. We will organize these metrics in 2 dimensions. In the left side, we have precision-oriented metrics. That is a metric that put the focus on the top of the ranking. For instance, precision at 10, or precision at a certain recall level, or reciprocal rank. And in the other side, at the right side, we have recall-oriented metrics that assign a similar weight to the top than to the bottom of the ranking. For instance, the Kendall or AUK. And we have another dimension, which is the publication date. So the date in which the metric was published in a paper. And there is an interesting phenomenon here, because it seems that the more the metric is recent, the more the researchers try to find some kind of balance between precision and recall. But this process is experimental by the intuition. So we will try to define a set of formal constraints in order to understand why this evolution of metrics along the time. So the first constraint is this. The idea is that we have here 2 system outputs, 2 rankings, and let's assume that they are exactly equal. But the green symbols means a relevant document, and the red symbol means that the document is not relevant. So suppose that both system outputs are very similar, but there is a swap in the second case. So, of course, if we assume a limited oxygen of the frogman, then the left output is better. Why? Because it is more probable to find the relevant document in the left distribution. Do you agree with this? Is there anybody? Does anybody don't agree with this? Okay, we all agree. This is a very basic assumption. So the idea is that prioritizing a relevant document above a irrelevant document must increase the score. This is a very basic assumption. But just with this assumption, we can discard some measures. For instance, in the case of precision and 10, the swaps happening after the limit of 10 documents are not captured by the measure. So strictly speaking, precision at 10 or reciprocal rank do not respect this constraint. But actually we could say, okay, but I know that in my case, in my scenario, the user will explore exactly 10 documents always. Okay, if you know exactly how your scenario will behave, you can use precision at 10. But if you are not totally sure, you should consider this constraint. The next one is quite similar. In this case, we have the same system output in both cases, but we make a different movement in each case. In the first case, we swap these two documents, and in the second case, we swap these two documents. So the question is, in what case we will obtain a bigger profit in this movement. If we assume the limited oxygen of the frogman, then we must say that the second movement is better, because the green document in the right side is more likely to be explored by the user. Therefore, it is more likely to achieve an improvement in terms of utility in the second distribution. So the idea is that documents at the top of the ranking have more weight. And with these assumptions, we can discard other measures like Kendall or AUC. But we have the mean reciprocal rank, we have mean average precision, we have Q measure, binary preference, and RDP. This is the next one. This is more subtle. Suppose that in the first case, you have only one relevant document at the top. Only one relevant document. And in the second case, you have 100 of non-relevant document and 100 of relevant document. So, what is the best one? Who says that the first one is the best one? Okay. And who says that the right side is the best distribution? Okay. So, okay, we agree, because of course we can assume that there is a limit of oxygen. So the frogman probably will not go so deep, so it is better at least to have one document. But somebody could say, okay, suppose that in my scenario, I know that the user will explore 1,000 of documents. So they should to change the constraint and say, okay, so one document, one relevant document is better than 1,000 of document after 1,000 of documents. In fact, we can generalize our constraint saying that there exists some limit. I don't know where is it, but there exists some limit. That is, for instance, maybe 1 million of documents is after 1 million of documents is worse than at least one document. So the idea is that there is a ranking area which is never explored by the user. I don't know how deep is it. So this is directly derived from the assumption that the frogman has a certain limit in his oxygen bottle. So surprisingly, the most popular measure, MAP and discounted cumulative gain and Q measure, do not respect this constraint. For instance, according to MAP, 1 million of relevant document after 1 million of noise is better than one document. But this is not a real problem in theory, because, for instance, if you use MAP in a TREC corpus, probably you will not find a case in which you have 1 million of relevant documents. So you can say, okay, I don't need to be worried about this because this situation is not realistic. But the fact is that, again, if you know exactly, if you don't know exactly your scenario, or at least if you can have metrics that respect this basic intuition, maybe it could be better. And this is the last one. In this case, we have 4 relevant documents after 4 non-relevant documents, and in the right side we have only 1. Okay? What happens here? If we assume that there is a ranking area which is always explored, then we need to assume that there is an area, a few documents. I don't know if they are 4, 2, 6, I don't know how little is this area, but I need to know that there is an area which is always explored by the user. If I assume this, I can define a constraint, and surprisingly, for instance, mean, reciprocal rank, or binary preference do not respect this constraint. So at the end, with this, we have defined the assumption of the frogman at the limited oxygen. We have analyzed the most popular method, and at the end, we have only 1 metric that satisfies all these 4 constraints. And why? This is because we are assuming, in our constraint, we are assuming a certain user behavior. And actually, RBP is a metric based on user behavior modeling. And at the end, they obtain this formula, which is basically consists on adding a relevance with a certain function which decreases the ganacy or the gain of relevance depending on the deepness of the position in the ranking. It's a very simple function, and in fact it respects the 4 constraints that we have. So in general, if you know, the recommendation is that if you know exactly your scenario, maybe you can use map or you can use a precision at 10, but if you don't have enough information about your scenario, it's better to apply a metric that respects theoretical foundation. But the next question is, why these constraints and not other constraints? So the fact is that it will be interesting to find another constraint in order to improve this method and find new methods. So we tried to do it. And we thought about this constraint. Suppose that in the left scenario you have 100 of non-relevant documents, and in the second system output you have only 6 non-relevant documents. What is better? The idea is that no information is better than wrong information. So if you only will return noise, then it is better if you return less noise. This is another constraint. And in this case, RBP fails also. So as far as we know, there is no any constraint that satisfy, or there is no any measure that satisfy all these constraints. But why? Because when you use, for instance, if you use RBP with a thread corpus, all the system output returns 100 or 1000 of documents, so you don't have this situation. But it will be interesting to find a metric that also satisfies this situation. So at the end, we have found, just thinking about a frogman and a bottle of oxygen, we have found 5 constraints, and we don't have yet a measure satisfying all of them. So the good news is that we have room for improvement, and we can maybe publish another paper about metrics.
It should be evaluated by a serial reviewer.
So is there any question about this? Okay.
When you say, we've been discussing about this before, when you say that a constraint is not satisfied, you have a strict idea of constraint. I mean, precision satisfies the greater than or equal constraint doesn't satisfy the greater
yes.
constraint.
And now,
can I say one thing as well? So it's funny. No, it's not funny. Actually, so you take the measures as being the things that vary, but you fix the relevance judgment. So if, for example, you take the relevance of a non-relevant document as minus an epsilon, and that epsilon is really, really tiny, okay, less than 1 over the number of the documents in the collection, then, for example, RBP would satisfy that constraint, because you would be accumulating negative values. So, it's, you know.
Okay, so we can publish another paper with a little modification of RBP. Yes, this is true. Sometimes the formal constraints are useful not for develop new different measures, but maybe to tune the current measures with a maybe with a smoothing or some change. So I'm trying to okay. Okay. Julio has talked about clustering, filtering, and ranking. In general, in most of information access tasks are managed as a single task, like clustering, filtering, or ranking. But in some cases, the real scenario is a combination of them. For instance, in this case, we have here the online reputation management. In this scenario, a company is interested on analyzing what the people say about them, for instance, in Twitter. So here, the first step consists of first retrieving every tweet talking or mentioning the name of the company. But the next step consists of filtering or discarding all the tweets that actually are not talking about the company. And after this, we have to cluster into topics the tweets in order to analyze the information. And finally, we have to rank the cluster according to the relevance. That is according to the priority in terms of reputation management. So here we have ranking, we have clustering, and we have filtering. And the question is that maybe we should evaluate all these tasks as a whole. Why? Because maybe poor filtering can be compensated by a good clustering. Or we have to take into account that an error in a cluster at the bottom of the ranking is better than an error in a cluster at the top of the ranking, according to the program. So the goal here is we will try to define a measure to evaluate all these tasks as a whole. Okay, and this is our methodology. First, we have to make a notation to unify the problem. After this, we need formal constraint in order to check the measure, and at the end, we will define the measure and analyze empirical results. So, in the case of clustering, we have a gold standard and a system output in which the documents are distributed in one priority level and in clusters. In the case of filtering, we have two priority levels in both the gold standard and the system output. And in the case of document retrieval, we have a ranking in the system output and a huge amount of documents at the bottom. And in the case of the gold standard, we have two priority levels. And again, the rest of the collection in the second level. But we can consider a general situation, for instance, like this, in which we have several priority levels. We have cluster in each priority level, and we have a huge amount of document in the last level. So here we have the notation for a combination of clustering, filtering, and ranking. And this is the task that we want to evaluate.
Enrique, it's 5 minutes. Just decide when you would
Okay.
like to stop.
Okay. So we need formal constraint. No, hasta aquí no entramos. This work is done. We have to find formal constraint for clustering, for filtering, and for retrieval. So basically, just in 1 minute, the idea is that the system output and the gold standard are a back of relationship. So we just need to. Después de la charla. I didn't understand. Okay. Do you want a coffee?
Okay, we'll continue in, let's say, about 20 minutes at 5 o'clock. And then we will complete this document.
The standard, we have a system output. And the interesting point is that in both cases, we have clusters, we have priority levels, and so we have ranking, we have clustering, and we also have filtering, because in the last priority level we have the rest of the corpus, which are discarded from the rest of the ranking. So the goal here is to define a measure in order to evaluate this problem that is comparing the system output with the gold standard as a whole. But and this is a very interesting problem because as far as we know, there not exists yet a measure to do this. There exists a lot of clustering metrics, filtering metrics, and ranking metrics, but not document organization metric. So, but the most important point here in this tutorial is to understand the methodology. We have annotation. So we have a problem formalization, and now we need a formal constraint in order to support the definition of the measure. But actually, we have done this work. Why? Because we can understand that clustering is actually a specific case of the document organization task. And filtering is another specific case of document organization, and the same for retrieval. So all the formal constraints that we have defined today are actually constraints for a specific situation of the general document organization task. So if we find a metric for this general task satisfying all these constraints, then your goal is achieved. Okay, in order to define this, we can do the same. We can do this. If we observe the notation, we can see that we can represent the distribution of document in the system output or in the gold standard as a bag of relationships between documents. Actually, we have only two kinds of relationships. We have priority relationships and clustering relationships. And all the information contained in the system output can be represented with a bag of relationships. So at this point, we could say, okay, let's just compute, for instance, the precision and recall of relationships. So we have a measure. We have a measure that to evaluate this general problem. In addition, we can express the precision and recall in terms of probabilities. Let's call reliability the precision. This is the probability of given a relationship appearing in the system output, the probability of finding it in the gold standard. And this is precision. This is reliability of relationships. But it is not so easy. Why? Because we started from a certain assumptions. That is, not all relationships and documents have the same relevance, very important in the evaluation process. Why? Because we said that the correctness of clustering relationships or priority relationship at the bottom of the ranking has less effect than the correctness of priority or clustering relationship at the top of the ranking. So we have to consider this. So precision and recall of a back of relationship is not enough. We have to add some kind of weighting scheme to these relationships, and so we need to add some parameters. And now we are in the crucial point. So we can take we have a problem because we have to define this. We have a huge amount of potential weighting scheme to define. But the interesting point here is that starting from the constraint that we have defined today, we can obtain at the end one or just a few possibilities for this weighting scheme. For instance, according to the deepness constraint, that is to the limit of the probability of finding of exploring documents at the bottom of the ranking, each document D has a weight which depends on its priority level. This is an interesting information. But in addition, according to the confidence constraint, we need to take into account the weight of all the huge amount of document at the bottom of the ranking. That is the rest of the collection. This means that the function, the weighting function that we have to apply need to be integrated for all this infinite amount of document. So not every weighting scheme satisfies this constraint. So we have now just a few options. In addition, in order to satisfy the deepness and closeness threshold constraint, we want to be able to say that the first n document carry out the W% of the weight in the evaluation. And in addition, in order to the clustering constraint size versus quantity constraint, we need to state that the weight of each document corresponds with the weight sum of all the relationships. Why? Because if we don't do this, we have the quadratic effect that Julio explained before. So I will not get into the details of this mathematical process, but the idea is that if we start from a few assumptions, you define a set of constraints, and you consider them, at the end you just have a few options when you define the weighting scheme. For instance, in our case, we use this function, which can be integrated for the infinite amount of document in the collection. And at the end, considering blah 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 the constraint, you have this formula with this parameter that depends of the W parameter and N parameters. The idea is that if you actually try to find another version with, if you change, for instance, if you remove this number, then you don't satisfy the constraint. So this is the idea. But now we have to Okay. Okay. And what happens when we apply this metric to a specific scenarios? For instance, what happens if we apply this metric in the case of clustering? The effect is that when we only have one priority level and we only have clustering relationships, we obtain exactly the B-cube precision at B-cube recall, which is the measure that satisfies all the formal constraints in the Julio's talk. If we apply it to filtering, it turns into the product of precision in both class and recall in both classes. So it has, empirically, it has a very interesting effect. We know that there is a very low correlation between measures in filtering. That is, Julio showed that the result can change substantially if we use one metric or another metric. Of course, we cannot find a metric which correlates with every metric simultaneously because they do not correlate to each other. But there is here a very interesting effect. Suppose that you know exactly the condition of your scenario. For instance, you know the gain or penalty for each correct decision. Then you can use the utility measure, for instance. Or maybe if you know exactly your scenario, you must use F measure or you must use accuracy or something like this. But suppose that you don't have information about your filtering scenario. What can you do? We have this metric that satisfies a lot of formal constraints. That this is a very strict measure. What does it mean? It means that if you have a high score according to reliability and sensitivity, you achieve a high score according to any other metric. Okay? The effect is, okay, if I use this metric, the drawback is that it is more costly to achieve a high score. But I know that if I achieve a high score, I can ensure that I achieve a high score according to utility, accuracy, F measure, or LAM. This is not free because it is more costly to achieve. But if I achieve a low score, I can achieve a high or low score according to any of the other methods. This is strictness, and we can quantify it. Actually, in our experiment, we can quantify strictness and we quantify robustness, which represents the capability of keep the same results across different data sets. The interesting point here is that we have defined a measure based on formal constraint, and the result is that it is more robust and more strict than the rest of the metrics. And what happens in the retrieval scenario? We repeat the same experiment and we compute the robustness and strictness of the metric. And then here appears an interesting phenomenon. If we parameterize the new metric in such a way that the 31st document has 80% of the weight, in other words, if we make the metric oriented to precision to the top of the ranking, then we are very strict but not robust. But if we make the metric oriented to recall, that is to all the ranking, we are more robust but not strict. Why? Because if we focus on the top of the ranking, we are covering also precision at 10. So we are stricter, because when we compute the strictness, we are comparing our measure with a set of other metrics. So, on the other hand, if we oriented to our metric to recall, we are more robust, we are less strict because we are not capturing the precision at 10. But we are more robust. Why? Just because we are considering more information. But actually, most of the work in the state of the art about metrics base the results in robustness, inconsistency across data sets, or robustness against noise. But the fact is that if you use more information, you are more robust. But this does not mean that your metric is more appropriate for a certain task. So at the end, how can we evaluate our metric? How to say that one metric is better than another? The only way to do this, that is the main idea of this tutorial, is that at the end we have to make a certain assumptions. We can define axioms or theoretical formal constraints from them, and then we have all the list or formal constraints for clustering, for filtering, and for information retrieval, and we have developed a measure that is able to capture all these conditions. And this is the best thing that we can say about this metric. In the future, we can find other constraints, and then we need to develop or improve this metric in order to capture new situations without losing the formal constraint that we actually satisfy. So this is the idea. The idea is the possibility of achieve better results from theoretical principles. Do you have any question? Thank you.
A small question. Is this something you have published already?
Yes, this is CIR 2013. 13.
13.
So the notion of strictness depends on the other metrics that you consider.
Mm-hmm.
So how robust is this notion? So how this is not a word game, but I really mean what happens if you start playing around with different metrics that you consider for your notion of strictness?
The thing changes. So we just take in our experiment, we just take the most popular metrics and we experimented with them. We didn't make experiment with different, but of course, if you the thing that I can ensure is that according to the strictness definition, if you add a lot of version of the same kind of metric, it not affect the result. But because I play with maximum and minimums but it is enough to have one sample of metric oriented to precision and another oriented to recall to have the effect of measuring the strictness. But of course, I suppose that if you change the set of reference metric, the result of strictness will change. But the idea of strictness is, okay, I want to select precision at 10, map, and RBP, and I don't know why. I don't know what of these three. So I want a metric that ensure a high score according to these particular three measures with a high score. This idea. Thank you very much.